We're going to start it on page 251. This is the part of the video where we're going to talk about triangle sum, the 30, 60, 90 rule, and exterior angles. And believe me, you want to know this relationship because this is a crucial part of what we do in geometry. It will not be just isolated to today or to this section of videos. It is massive. So pay attention to the 30, 60, 90 conversation. In case you're wondering, the learning goals back on page 247 identify that we're going to identify and draw exterior angles of triangles and midsegments. We're going to continue the conversation on writing a conjecture as a statement and the converse and pushing through that. We should highlight or make mention of what things that mathematicians do. So mathematicians, like you are practicing, we're going to reason abstractly and quantitatively. We're going to construct viable arguments, and we're going to critique the reasoning of others. In the triangle sum 30, 60, 90 degrees and exterior angles activity, we're going to construct a new diagram and investigate the relationships and make a few more conjectures about triangles. Remember, a conjecture is a statement, a rule that appears valid. You do need to formally prove it, but certainly we can get a lot done with conjectures, rule statements. Let's construct circle R and circle S. They're each going to have a radius of RS. Now, I'm using my pro compass because the school ones make me mad, but the school compasses work when you tear this paper out of your book and then save it for the future. Make your compass be that wide. And so for me, with the pro compass, it's easy enough to do. I just spin the little wheel, and then I'm going to draw a circle. If this isn't working on the space that's been given with the school compass, then get a sheet of paper, something fresh, and make a bigger line segment on there, and then draw your two circles. But the key thing is that you have to keep the circle the same size. You flip the compass around and draw a second circle. Centered at S, the radius RS does not change. And voila, where the circles cross, we're going to label that as T, and on the other point, label it as V. Okay, that's it. That's all they wanted us to do, number one. All right. Oh, number two, draw line segments to form triangle RST. So your straight edge, RS is already drawn in, but we need to draw in the other two line segments, RT and RS. Or I'm sorry, TS. There we go. Explain why the triangle you created is equilateral. Did you think about that when you were creating it? This is absolutely a test question. What does this tell you about the relationship between point T and the end points of RS? So there's two things that we're going to say. The first thing we're going to say is that triangle RTS, or they're using ST, triangle RST is equilateral because T is on the radius of circle radii. It's actually on crossing radii of circles R and S. Since these circles are the same size, my writing is looking atrocious right now. Since these circles are the same size, that means that RT and ST are congruent. Now, they're also RS. Oh my gosh, I can throw that in there too. There we go. All three sides are actually radii of circles. The radius, from the center to the edge. And when you have the same size circles and their radii are created, then if they're all the same length, equilateral triangle, because all three sides are the same. Previously, you learned that the perpendicular bisector theorem states that if a point is on the perpendicular bisector of a line segment, it is equidistant from the segment's endpoints. That was like lesson 1 or something, or even like, module 1. Go back a ways. The perpendicular bisector theorem states if a point is on a perpendicular bisector of a line segment, that's P. That's the hypothesis. P for hypothesis. There's a P in the word hypothesis. Then it is equidistant from the line segment's endpoints. That's Q. Q for conclusion. Hypothesis, conclusion. To write the converse of the perpendicular bisector theorem, you switch the green and yellow. You, instead of saying if P then Q, the converse is Q implies P. So we're going to say green, and then we're going to say yellow. If, let's say what it is. If a point, if a point, you shouldn't lead off with a pronoun. You should say the noun first. So instead of saying it, we're going to say the point. If a point is equidistant from the line segment's endpoints. Let me write all that. That's the conclusion of the original statement, but the converse says switch them. Then, now we can use it instead of a point. Then it is on the perpendicular bisector. That's the converse. I should finish it out of a line segment, but I'm just going to say ... like you got that part. Let's consider the converse statement. Is that absolutely true? Well, construct the perpendicular bisector of segment RS, and then label the point where the perpendicular bisector intersects the line segment as point Q. Remember those rules. Scrub back and forth in the YouTube video. Let's go up here. To construct a perpendicular bisector, this is the construction of a perpendicular bisector. Two circles, same size, that cross. So if you connect where they cross, T to V, careful, careful. I can do a better job than that. Barely better. If you connect where they cross, that line is the perpendicular bisector, and they want us to label the place where it crosses RS as point Q. All right, now let's go back to 4A. Construct the perpendicular bisector, check. Label the point where it intersects the line segment as point Q, check. Determine whether the converse is true. If this converse is true, what can you say about points T and V? Remember, the converse says if a point is equidistant from the line segment's endpoints. Yeah, that happened. We created an equilateral triangle. Equilateral, equidistant, it all lines up. So, yes, the converse is true. Now, what that means is that you can draw a line through points TV, the line drawn through T and V creates the perpendicular bisector. So something that, when you do that construction with the two circles that cross and then you draw the line through them, well, not only when you draw the two circles that cross, that creates two equilateral triangles, a top one and a bottom one. But if you connect the endpoints, connect the top triangle's vertex and the bottom triangle's vertex, that's T to V, that actually does end up creating the perpendicular bisector. So converse is true. There are other things we need to talk about. Remember, this is part one of a 4-part video series on activity 2, so stick around for those parts. Thank you for watching this video. See you on page 252. Thank you for getting better at math, one day at a time.